Good morning, good evening, good afternoon, everyone. My name is Nancy Lindsey. I'm the Reliability, Maintainability, and Availability Subject Matter Expert, or simply the RMA SME, and also the R&M Tech Fellow for NASA headquarters. I'm here today to talk to you about model-based engineering, especially model-based safety and mission assurance, and what the use case is for risk-based safety and mission assurance at Goddard Space Flight Center. In case you don't know, NASA is comprised of 10 specialized centers. Each one has their own mission and their own specialized engineering and safety and mission assurance. The activities at each center are specialized, and the development, implementation, and oversight is for the betterment of all humankind. Our space innovations reach both the science community as well as the general public each and every day. So I come to you from Goddard Space Flight Center. It's located here in the DC area. You see that up in the upper right-hand corner is the picture of our center. But more importantly, Goddard Space Flight Center is focused on, just to give you an idea of where I'm coming from, is focused on earth science, heliophysics, and then also space weather. So we have very many missions that are up in orbit at this time. We operate all of your weather satellites that you get your hurricane and tsunami forecasts from. Goddard started its work in 1959, and we have been responsible for the development of the James Webb Space Telescope, which I'm sure some of you have seen some images from. And then on-orbit servicing, and including balloon and sounding rocket missions from our satellite site in Wallops Island, Virginia. So we are actually a launch site, as you see in the middle of the screen there. We actually have launch vehicles coming out of our center as well. So to enable all of these special missions, we have a safety and mission assurance department, and that's where I come from. And our mission is to reduce the risk of exploring the Earth and space and beyond. It's a highly respected field, and it continuously characterizes the risk and applies the requirements in a tailored fashion so that we can do the best and be the safest missions and be the most cost effective and not put both the public and or our astronauts or our space in general around the Earth in jeopardy at any time. And we always shoot for, of course, 100% success, or as NASA like to say, failure is not an option. So how do we do that? We use risk-based SMA, and that is where we start to get into the use case, because there are challenges as we move forward in the environment of doing all of these missions. We have to make sure that we continue to be able to implement, to provide the oversight, the decision making that's needed to make sure these missions are a success. Again, failure is not an option. So in the changing environment of space, we have reduced budgets. We have increased demands on the spacecrafts. We have reduced size. We have larger size. We have longer duration missions. All of this requires that our safety and mission assurance teams, the disciplines you see on the right-hand side of the screen, communicate with the design teams and the risk management teams, the big circle on the left-hand side of the screen, and we pass data. But if we are not timely in passing that data, we can't be effective in implementing fixes for the design or general safety of the mission itself. And we may not have as successful a mission as we might like. So timing and consistency is important. Failure susceptibility and tolerance, I've said a couple times now that failure is not an option. Well, we want to make sure that if there is a situation where we have, as we like to say, an anomaly and an unexpected event, potentially even a small system failure, that we can fail over. So we want to make sure in a graceful way, we want to make sure that we maintain that mission success. We do that through quality, software assurance, safety, and reliability. So in order to do this information passing, traditionally we're doing a lot of meetings and a lot of information sharing, but timing is very important to be sure that we provide the value to the missions when they need it and when they can take action on it. So in doing that, we want to make sure that our timing is as far to the, as you see on the right-hand side, the project timeline. We want to move that timing of knowledge over to the left so that we can have greater influence. Because once you start building a mission and the design is solidified and you, quote unquote, start bending metal, it's harder to make changes, even if it would make the system more robust and more resilient. So we want to make sure that we have the most influence as possible. That means we have to make sure that we have the knowledge as early as possible. How we're doing that, you see we have digital transformations on the left-hand side. We have electronic CM, electronic work instructions, or our procedures. We are expanding our lessons learned. We have automatic requirement generation, but we also have analysis that we want to automate. And that's where digital twins or model-based safety and mission assurance comes in. We want to make sure that that can actually move our current state from the blue line all the way up to the dotted yellow line, and we get to be the right in pace with our design teams, and that we solve the what we call the N-1 problem, that the design teams are one iteration of the design before us. And how can we do that? The best chance we have to do that is with model-based mission assurance. And in that, we want to, the use case for Goddard Space Flight Center is to develop an understanding, this is the top line, conduct a feasibility study, and then utilize model-based safety and mission assurance on actual missions, and then institutionalize that use as we go. All, as you see on the right-hand side, the influence arrow continues to advance over and over and over again. Just the more we can optimize, the better we can do, because it's all about timing and having the right data at the right time. So what we've done is we've already looked at what model-based engineering is out there in the marketplace. We've down selected to two different tools. We have Magic Draw and MADE, and we've done a feasibility study, and we've completed both the RMA, the reliability and maintainability processes, and we've also done the system safety processes through this, what we say as a feasibility study. And you'll notice that we emphasize in the notes there that safety and mission assurance at NASA has not been broken. You haven't seen a lot of failures. So we are trying to make sure that we get consistency, efficiency, and accuracy increases as we move forward in this feasibility study. Again, to make sure our missions get the information as quickly as possible, and we have the most influence and can make the designs and the missions as safe and effective as possible. So in our feasibility study, again, we used a simple methodology of using simple missions, or actually pieces of missions we call subsystems. We used a mechanical subsystem, an electromechanical subsystem, and a electrical subsystem to make sure that that didn't influence our designs. We went through this test case for reliability, and then we also used a similar test case for system safety, and we'll go through those as well. The propulsion, of course, is our mechanical. Our celestial ACS, or our attitude and control block diagram, is our electrical, and then the Cappy brick system that you see on the right is the electromechanical, has both systems within it. And then we also created, because we want to make sure that scaling the missions from a subsystem up to a full mission doesn't cause us a problem. So our use case, of course, in the long run would be an entire mission. So we wanted to scale up as well, and we have done that successfully. In particular, that piece We were successful in accomplishing that with MAID alone because the SysML and Magic Draw combination did not provide the utility that we needed to actually create a full mission state in an effective and efficient manner. So we were able to do this with MAID, and as I'll mention later, we have an entire reference model that can be used. We have a MAID model that we can share with anyone who requests it. It's out there for public domain, and it is an entire spacecraft. So we can actually share that with you at any time. Just send me an email and explain your use case, and then we will send you the model. That gets us to the outcomes of what we have found in terms of these studies, and takes us through that sequence that you saw, that if we show that we are feasible, that we've increased the consistency, efficiency, and accuracy, then we can move forward and institutionalize the use of model-based and pretty much down select our tool choice to be the most effective we can do. And feed back to our vendors what we need those tools to do if they don't do it already. So in terms of the reliability maintainability study, we found that if a modeling environment allows the discipline to do what they do now with libraries and known information, then we can increase the consistency or become what we like to say analyst agnostic. Simply put, that just means whether you have someone like myself who has close to 40 years of experience or someone who has 5 years or less experience, they analyze and look at the design and they come out with the same answer. And that allows our missions to be, one, more cost effective in doing the analysis, and two, it allows them to trust the outputs no matter who is doing it, and we don't have to have the same person assigned multiple times. Thankfully, the MAID software has these libraries already for reliability, maintainability, and availability, and the ability to customize these libraries. So it was a natural input to the system and to our process. We were able to use the libraries to create the failure modes and the characteristics inside of the model for these subsystems and execute our reliability probability analysis, our availability analysis, our FAMICA analysis, our fault tree, our single point failure. And then we looked into, but we didn't execute the maintainability analysis. So we just had to downscope what we did in this feasibility, but we did understand that that was actually a potential capability of MAID. In terms of accuracy, if a modeling environment supports all the analyses accurately, if a modeling environment produces a output that cannot be trusted, then it is not going to help us with accuracy, consistency, or efficiency. And in particular, not to model-based safety and mission assurance, model-based engineering is currently trying to develop a lot of things inside that Magic Draw environment, but we found that the current plugins there, they create fault trees with logic errors, which that is absolutely cannot happen. We don't want anything that creates extra work for us. And that's where when we ran these same analyses in MAID, we found that we produced an accurate prediction. We produced an accurate availability analysis. We actually, everything matched what we did in the traditional sense. So that was our metric that we saw that really did match, and that understanding and knowledge was heightened. That when we looked in and we used the libraries inside of MAID, and we put the same failure characteristics and used the failure tree that's inside of MAID called the failure diagram, it was easily understood. And we went, oh my goodness, some of those failure mode causes that we didn't consider as plausible really are plausible. So we actually enhanced the traditional as well as doing the feasibility study. Our engineers learned more about the mechanics and the physics behind it by being challenged to say, does this really apply in our case? So it became a better analysis. It wasn't even just accurate, it became better. And our analysts became better. And they were able to focus on the analysis, not actually just putting together a large spreadsheet of failure modes and trying to get everything and trying to have meeting after meeting, going through the design and trying to figure out what happens. By being able to put together a simple wiring diagram in the MADE model, as you see in the center there, it was a natural flow of the data, the power, and the material. We could show those flows right through a natural way of engineering and creating the model. It wasn't some sort of special new way of modeling to learn. It was just the ins, what we say is the goes intos and goes out of each element, and then diving down in. So it allowed us not to have a lot of time to have training. And that gets us to efficiency. If the modeling environment can't be understood by both the analyst as well as the team that's using it for the next decision making, then you don't have the efficiency, and you don't have even potentially the accuracy. And we found that you have to be able to do it without repeating efforts. What we were able to do is characterize the system once in that wiring diagram, and then run all of these analyses from one button push. And that was a big increase in our efficiency. We didn't have to remodel the system in a separate tool. In terms of, again, in our feasibility study, we had the magic draw as the alternate, and that we actually found, besides having some of the logic errors in the fault tree, we would only go in one type or one point of view for the reliability. It would either be inductive or deductive, and would require modeling twice inside of SysML and Magic Draw to get both points of view, which is what we need to make sure that we have mission success. And in MADE, we didn't find that. So we were able to really take an advantage of efficiency. And in terms of efficiency, just giving you a benchmark of what we found, we were able, in the general sense, being able to create a MADE model and produce the artifacts in a matter of a few weeks, from not knowing the system at all to producing the accurate artifacts. Normally, that takes about 2 to 3 weeks, maybe a month per analysis. So again, we were able to do this in a much quicker time than traditionally. And just for comparison, we were able to do the same thing in SysML and Magic Draw in 6 months. So it increased our time, which is an absolute showstopper for us. So after phase 1, it was obvious that we were able to get on our curve, and we were able to move the project time. We were able to do and be able to influence much earlier if we used a tool that was ready to go out of the box. And that's what we found MADE to be. Now, we also found that modeling is a great thing in general, but MADE was the best tool that we to use for Goddard at this time. From these, and you see those references in the blue takeaway box there. Those are the papers that we have available, and we also have tips available. So if you want to get into the modeling, we have released all of these publicly, and we are able to share the tips, and you can follow our step-by-step guide on how to model a system inside of MADE, which also covers Magic Draw, but the tips are, we recommend that you focus on the MADE tips and use MADE. Otherwise, you're going to take longer instead of a shorter time. So with that, I said all three were released publicly. The one that ends 9990, that is the detailed report that is restricted to U.S. citizens only, but the rest of them are for public release. And I've said this already once, but we also upscaled to make sure we were a full mission. That it wasn't a limitation, that model base wasn't just good for an individual subsystem. And then when you tried to scale up to a full system, it fell apart, or that the time got so enormous that it broke those 3 tenets for trying to improve, which was efficiency, consistency, and accuracy. So when we saw that we could, we actually made a generic model. So we took the NASA-specific designs out of this model, using the model as it was, and then we made it more generic. And we were able to create a reference model that now is shareable to anyone that is interested in modeling a spacecraft or any complex system. And now you can actually take that model and jumpstart your modeling process by using this reference model that's provided in MADE. And again, we can use this for our own engineers as well. If we have a reference model, we can start the next mission with a reference model and move forward and customize it to the particular mission. So again, we found that this capability and this ability to share a reference model like this that's really customizable, and you don't lose a lot of information by doing any copying or anything. This provides us with the next step in efficiency. It's not just per emissions efficiency, but now we can do more and more missions more and more quickly. So phase 2, we talked a little tiny little bit about that. That's system safety. System safety looks at the hazards, those things, and protects the system against it. So it's almost the opposite to reliability. Reliability makes sure that we have enough to make things work. System safety makes sure that things don't work at the wrong time. We don't want to deploy large solar arrays when we're inside a narrow launch vehicle. So we want to make sure that they don't go off when we don't want them to. And that's where system safety goes hand in hand. So that's why we used that as the next phase. We used exactly the same models as we said earlier. And then we ran the same tests. Can we produce the information that we need for system safety? In terms whether they have enough inhibits, meaning that they don't deploy something when they're in a launch vehicle or open valves or do anything that could cause a hazard. Providing safety data packages, which are details of the system and all of the nuances and what hazards each and every item potentially has the ability to create. And then hazard reporting. All of these things are what our system safety people our engineers have to do in order to influence and get the system with the ability to launch. If we don't do this, we won't be able to launch. So they were in the same boat. They're not broken. They just needed a way to be more consistent, more accurate, and more efficient. And in this case, we ran the same kind of modeling sequences, and we only had one tool that was able to do it. MADE allows us to do hazard analysis. Magic Draw doesn't. So now you can already see that regardless of even the results of phase 1 that were fantastic in terms of MADE, we want to model once. We want to share the models. We want a complementary team. We don't want the system safety people to model and the reliability people to model and then the quality people to model. You can hear as if we create more and more models, they're going to become inconsistent. One's going to be not representative of the true system. We're going to be out of sync. The information we provide to the mission teams is going to be worthless because it's not going to be consistent with either their design or reliability and safety are not going to be talking about the same mission. So we were able to use the Europa propulsion subsystem to run our system safety tests, and we were able to, with some tailoring, because MADE was not designed to support NASA specific outputs in the specific way NASA does it, hazard analysis, but it does do hazard analysis. So we were able to use the general capabilities out of the box of MADE and perform analyst agnostic information and analysis inside of MADE and get out all of our products that we need, including, that's not listed here, a compliance matrix, but we'll talk about that in a moment. And we see the potential to actually go even beyond what we saw now that these reports are, again, once you model, put the information in, you can get these out with one button click. We actually there's the ability to put in customized libraries. Now, there are hazards inside of MADE now, and they're advancing them with our inputs, which is a great piece of the interchange between the customer, which would be NASA, and PHM and Siemens. We're able to influence as they advance. Can you include this functionality, which is more close to how NASA needs it? So we were able to start influencing how the advances in this hazard side would be actually done. And one of the potentials is to actually produce this NASA safety library where we have standard hazards. We have human factors hazard or contamination, explosions, all the circles you see, and then all of those consequences or the details of those hazards. So you have arcing and bent pins, and you have fire is caused by chemicals. So there's all sorts of connections. These are natural connection inside of MADE as we go through the functional diagrams. And this would be almost impossible to model or have a library developed with similar characteristics in other tools. So we saw that there's definitely a potential for efficiency to increase with these specialized systems and the ability to do a reference model. But further beyond that, as our systems get more and more complex, the burden is on the system safety engineer to be able to visualize and conceptualize a very complex system and be able to forecast whether the hazard will get through the system or not, and create it the potential hazard will get through the system and create an actual hazard. And the more they can influence and make it up front and optimize whether or not, because again, the reliability or mission success and safety are at odds. Make it safe, it doesn't do what we want it to do when at the wrong time, but if we make it too safe, it won't do it at the right time. So we have to make sure that there's a balance there. So we don't want to over safe the mission and we don't want to under safe the mission. So that's where the capability inside of MADE to simulate failures or inhibit losses is a great asset. We were able to, and I'm going to play the video here in a moment, but we were able to insert or simulate two failures. We had a latch valve, and a commanding failure. So we actually commanded the fuel line to open, and then we had the latch valve also fail. So those are two inhibits to make sure we don't get fuel on the ground during launch, because that would mean a really bad day. So imagine that this is the subsystem, and then it goes up to the larger system. But imagine you have this fuel inside a small portion of a larger and larger and larger system. That is an important piece, because it's easy. You'll see that, oh, you could do this in your head and with this drawing the way it's shown here and what we'll go through. But when you have systems on top of systems on top of systems on top of systems, you tend to put the inhibits down at where you understand, and you may be over inhibiting the system or under. So in terms of the simulation, you'll see that we first we make sure that the top latch valves are closed. We insert the first failure of commanding the fuel to flow, and then this latch valve is also open. And any item that's sideways shows that we didn't have fuel flowing through those, but any up arrow, the fuel is flowing. So so far we've had two faults, and we come through and we go up to the system level, or the subsystem level in this case, and we show that fuel is flowing. It flows to the next level, but the final output, we have one more inhibit, which is the actual thruster itself. It's closed, no fuel flows. So we can see very quickly, go insert a failure or a loss of an inhibit down below, and you can see it up above. This is a time saver beyond belief to be able to do these simulations and be able to go through the process. It increases the accuracy of the system safety engineer and the efficiency, and we can optimize our designs and not make them overly safe or underly safe. So where are we going? Our use case for model-based in particular MAID, since that is the optimal situation for us, the best tool to use at this time, is create a modeling process that supports multiple disciplines, making sure that our systems engineering and safety and mission assurance are working together, that we both understand the model together. That means that we have to insert performance requirements, clearly define the responsibilities of each modeler and the outputs, complete the modeling and sharing information back and forth, and then verify and refine the models and share that information to future missions. Now, this is all possible within MAID because MAID has most of the things that we see in the pie-shaped diagram on the right-hand side, that we need an intuitive GUI and reporting, that we don't want to spend most of our time training people how to model and how to understand the model or create special views to understand the model. I pointed out earlier that the wiring diagram is a natural engineering tool. Our engineers do that in PowerPoint. We do that in all sorts of different things. The ability to take CAD models in, the ability to output things back and forth, to create reports in one button click. That's an important piece of any modeling tool, and MAID has that. So that's why we are saying right now that MAID is our best solution at this time. Reusable and importable system knowledge. We can import things. We can import CAD. We can import previous analysis. We can import requirements. We can do automation and simulation. We can do the discipline knowledge is there. We can use what's in the tool, the out-of-the-box libraries, and then we can make them customized to NASA. There's special NASA failure conditions and environmental things that no one else would think would be a cause of a potential failure, but for us it is. And then error checking. This is a no-brainer for any tool developer, that when you have a modeling tool, that you have to provide the user with error checking, inconsistencies in the actual user making a model. MAID has this, and regrettably the SysML magic draw that's highly promoted by some among NASA and other groups doesn't. So now you have the problem with garbage in, garbage out, and that doesn't happen in MAID because you have a little warning set and you can see exactly what the information is, as well as configuration control that helps us understand when this multidisciplinary team who's doing what to the model, and ability to select and customize the system behavior and knowledge capturing. That's an important piece. I provided in the backup to these slides, each one of these breaks down to specific tooling capabilities. Again, we were in the long run, we were able to say that yes, for Goddard Space Flight Center, the best tool for safety and mission assurance to use in terms of model-based safety and mission assurance at this time is MAID. But if the enterprise or anyone else decides that they want to not use what we're recommending, we're also giving a list of what are the requirements any tool would really have to have. So our mission wasn't to choose a tool, but we did end up choosing a tool because it became a no-brainer to we can't go backwards in efficiency and consistency and accuracy by going to model-based. We want to increase our influence, and we have to make sure that happens through the information. Now you'll see the numbers on the bottom. The reference numbers have changed a bit. The two top ones are both the phase 1 and the phase 2 study results, and then you also have your modeling tips still there. Those are except for the 990, all public domain documents. You can see exactly what we did. So our path forward: continue through, do a full system safety model of a full mission, move into our phase 3. We didn't do all of safety and mission assurance yet. We still have software assurance and quality engineering to add to our list, but we feel that that's definitely doable inside the tools we have right now. And then make sure that we can utilize and model-based systems engineering and model-based safety emission assurance on a full mission to make sure that we go up on this influence and consistency and accuracy curve. We go to the left on that curve as long as we are consistent, accurate, and efficient, and that is important. And continue to work with our tool vendors such as MAID to customize the tool for capabilities it doesn't have that we need, and then also help us with any additional customizations we need to do on our end. So are there any questions? Again, I mentioned the backup. There is some specific modeling tool recommendations as we move through. The majority of these are already supported by the MAID tool, but these are the global set, and they're highlighted with yellow, no highlight, and yellow highlight to show the differences between the efficiency, accuracy, and consistency. So I offer again, are there any questions?